Okay, so just a reminder, let's just recall positional multiplicity. Okay, positional multiplicity was, something that looked like this. I am only interested in where all of my molecules are located, so it could look something like this. Okay. The other thing is I could also have some different categories, right? So I'm calculating positional multiplicity W. M is the number of spaces I have, okay? And N sub T is equal to the number of different categories I have, okay? And so that includes both, the blue ideal gas molecules, but if I have red ones, some other type of gas that I could distinguish, or some purple gases that I could distinguish. These other categories would be there as well. And our final category is always going to be empty spaces. And when this gets really large, when the numbers get large, we use Stirling. Okay, so the important thing to consider, though, is that these molecules also have kinetic energy. And potential energy if they're not an ideal gas anymore, as soon as it's a protein running into another protein. Okay. So these molecules have kinetic energy, okay? So they're moving, and potentially, they have potential energy if it's a non-ideal gas. Okay? So these could be ideal gas, or they could be a more complex, biomolecule, like a protein. For the sake of describing energy distributions in this class, we're just going to call energy U, okay? So that kinetic energy, we're really only going to consider kinetic energy. We won't consider potential energy, okay? They have kinetic energy that we'll call capital U, and it's not necessarily the same for every molecule. So what was the other way to, the other definition of temperature? Temperature is a measure of what? Of average kinetic energy, okay? That is important, okay? Temperature is a relative measure of average kinetic energy. These do not all have to be at the exact same kinetic energy, okay? So we could have, tell me if I showed a figure like this before. I thought I did. So it showed something like this. It had a bunch of little lines, and it was like translational kinetic energy, and then there was bigger gaps for like rotational potential energy differences, and then maybe vibrational was bigger. Did I show a figure like that before? Yeah, on the slides. I didn't draw it. Okay. Well, there are different energy levels that these molecules can be in, okay? By quantum mechanics, they are quantized, they are discrete, okay? So that's why we've drawn them with this sort of gap between them. You're either in the lowest level or the next level up, okay? And this is just, I'm moving faster with velocity, getting, put in some heat, raise the temp, and now I have a little bit more kinetic energy. I might be able to move, that's fine. Rotational potential energy was, what were our examples there? We're actually doing what? First of all, to have potential energy, I have what? I'm sorry? Okay. Yes. That's not a wrong statement that if you have potential energy, then you can have the ability to do work. But thinking about an ideal gas versus something else. I have bonds, okay? I have chemical potential energy stored in my bonds. And so I can rotate about those bonds, or we said if we actually start vibrating or stretching some of the bonds, that's going to take even more energy to get to the next level, stuff like that, okay? I swear I showed that figure. We'll see it soon, okay? So we can describe these energy levels, and again, this is just sort of drawing them as lines like this is a way to give us a visual, like a picture. Doesn't necessarily reflect anything other than when you get a question about energy distributions and the first thing is draw a picture. This is how you draw it. You draw lines and label your energy levels. Okay? So let's say we have some sort of, ground energy state here. And then we have some higher level, and we could have maybe 4 molecules here, 3 molecules are in this level, maybe 1 molecule's here, doesn't matter, okay? So now, to do multiplicity, M is now equal to the number of molecules I have, okay? This is distinctly different from what's going on over here, okay? This was total number of spaces, this is now the number of molecules in my system. And N sub T, my categories, are now my energy levels. Okay, from 0, 1, 2, 3, this is increasing energy U. Okay. So these are my levels, 0, 1. Okay, and so when I want to, let's say, write the multiplicity for this one, what goes on the top? 8 factorial. I didn't really think about how many dots I drew. Okay? In the 0th level, I have 4. In the first level, I have 3. Next, I have 1. Any future levels are all 0. I don't need to write anything. Okay? This is fine right now. There's a small enough number of molecules that I can count them. Eventually, we're going to get to a number of molecules we can no longer count and track. And so instead, what we need is the probability of being in any given level, okay? That's what we're building towards. And keep in mind, with the ground state's always going to be given by a 0 energy. And this is where everything wants to be, right? Things want to minimize energy. Keep that in mind as we go forward. I now feel like I can't draw exclamation points to emphasize things because it just always looks like a factorial now. After a letter, I think you'll be fine, but I've done it sometimes after a number, like, the probability should sum to 1, and then I'll draw an exclamation point. I'm like, 1 factorial still is 1, but now I panic. Okay, so let's talk about some rules, some assumptions for energy distributions. Okay. Energy distributions, they describe, let's see stuff, okay. They describe the population of molecules across possible energy levels. And we have some simplifying assumptions. So the first one, 0 will just be, and originally include this one, that energy levels are quantized and discrete. Who's taken quantum mechanics? The MSc department made us take as sophomores this quantum physics class that was taught in MSc. None of us ever had a clue what was going on, pretty much ever. But we drew a lot of energy distributions. I know that was happening. I know I was exciting photons into new electron shells and stuff. Didn't end up being what I went on to do. Right? Went a little more bio with it. But. Okay, so let the energy levels be evenly spaced. Number 2, let the level, the lowest level, or ground state, is always 0. Units are arbitrary. So we have sort of arbitrary units. It could be kilojoules, or joules per mole. Maybe I'll give it to you, maybe I won't. It won't matter. Okay, you could just write energy units, depending on what information you've been given in the problem. Okay, so what this means is U sub 0 is equal to 0, U sub 1 would be equal to 1, U sub 2 is equal to 2, or it could be something like use of 0 is equal to 0, use of 1 is equal to 2, use of 2 is equal to 4, these distances are the same. Now I will say this, this is really suitable for introducing all of this stuff. Do you think evenly spaced energy levels is real life? Yeah, obviously not. And there will be an example problem on the homework where it's not evenly spaced. So just what you'll use is the energy values given to do your calculations rather than making the assumption. No molecule can occupy an energy level higher than the total energy of the system, which we're going to call U total. So if, for example, like your total energy was 4, there's no single molecule in the 5th energy level. It's just not possible. And then our 4th assumption, energy is always conserved. What is the other name for this? First law. First law of thermo. Okay. And so the way to show this would be the sum over all of the levels from the ith level equal to 0 up to t number of total levels is n sub I times the energy of that level. U sub I is equal to U total. Okay. So this is the energy of the ith level. And this is the number of molecules in the ith level. With 3 molecules and 4 levels. And they all start in ground state, let's say. And then this is again the direction of increasing energy. And then let's say I add 2 units of energy, probably heat, whatever it is. How can adding the 2 units of energy happen? There's 2 ways. What does this look like? Someone can shout it out. What would be a possible option for putting 2 units of energy into 3 molecules? Move one of the dots to the second line. Love it. Second energy state, and the other 2 stay in ground state. Okay, and what is the other option? 2 move up to the first level. Okay, those are your 2 choices. Right? Okay, I've put in 2 units of energy. U total. Let's just check that everything looks good. So U total is going to be equal to 2, and it's going to be the sum of the number of molecules in a given level times the energy of that level. So this will be, for A, it's 1 molecule in the second energy level, plus 2 in the 0th equals 2. Or for B, this is, I have 2 in the first energy level, 1 plus 1 in the 0th. Sum them all up, they're both still equal to 2, so everything's conserved, everything looks good, I'm happy. Okay. So now let's consider the number of ways that A and B, these sort of configurations could happen. The number of ways is always, I'm asking for multiplicity. So for our A case, we could have the first molecule pops up into the second level and the next two stay down in the zeroth, or the middle molecule is in the second energy level, okay, and the first and third stay in the ground state, or the last molecule could be the one that moves up to the second level. Okay? So multiplicity is equal to 3, and if you want to go through your factorials just to really make yourself happy, 3 factorial is the number of molecules is on the top. I have 2 of them in the zeroth level, none are in the first, 1 is in the second, none are in the third. We know that these drop out to a 1, so they don't really need to be there. But this would be 3 times 2 times 1 over 2 times 1 times 1 times 1. This is 6 over 2, this is 3. Okay. What is multiplicity for B? It's not 6. Here it is again. How many molecules do I have is on the top, the energy levels, and how many are in each of them, each of the categories. Do you have a question?
Yeah, can you describe how you did the bottom history? Is that 2, 0, 1, 0?
This is 2 factorial for the zeroth level, 0 factorial for the first, 1 factorial for the second, 0 factorial for the third. And like I said, going forward, you wouldn't necessarily bother to include the 0 factorials. Right? But those were for all the energy levels, okay? From ground state to the third level. So what's the multiplicity of B? 3, okay? It's also 3. So then are A and B equally likely to happen? Given your knowledge of multiplicity and entropy, what would you say? Yes. These have the same multiplicity, okay? These would have the same entropy by our statistical definition. They are equally likely, given that we're just trying to maximize multiplicity, but they have the same. As soon as we get into bigger systems, that stops really being a concern. Again, it'll always be obvious kind of what we're moving towards. So Boltzmann's statistical definition of entropy here is sort of the best possible calculation that you can have. This is the best possible calc for entropy. Multiplicity in real life would combine both positional and energetic. Okay, so you think about where all the energy of every single molecule is and the position of every single molecule, and that's how you would decide what the maximum multiplicity is. We are not going to do that. They'll always be separate in this class. I'll only ask for one or the other. And moreover, in real life, it's impossible to track all of those things. Okay? So again, if you could actually get multiplicity for every molecule, this would be sort of like a perfect measure of entropy, but that's not real life. So what we have instead is delta S equals Q reversible over T, our classical definition. Okay. I actually wrote on my notes here, this one sucks. Maybe some better description of that would simply be that this assumption is not real, right? The reversible case really isn't true. We know that delta S is always really bigger. Okay, so the equal sign isn't super meaningful for us. And we can only do a change. we're using heat flow, so we have to do a difference in entropy. We can't get entropy for a given state with this value either, right? So it's, it's only for change. So it's just not as informative, okay? Easier to measure, yep.
So are you saying that like the molecules themselves are distinguishable?
Every molecule in real life would be, you could tell it apart and you would track everything it does.
Okay.
In some cases, you might go like, oh, all of this particular protein, we could treat them equivalently, but it's different than this other one, which is different than this other one. So then what we want to introduce now is something that falls in between, okay? Something for when we have really big numbers of N, really big numbers of molecules, so it's really difficult to calculate multiplicity, it's difficult to calculate entropy. So what we have then instead is the probabilistic definition of entropy. If you look that up, if you put it into Google, the first thing that's going to come up is Wikipedia's page for information theory. If you're curious what it's built on. And the equation itself is S is equal to negative capital N, Boltzmann's constant in case of B. Okay, these are being multiplied, multiply this by the sum of p sub I times the natural log of p sub I, okay? So this piece here should look a little bit like Stirling. This is built off of the same approximation as Stirling. Okay. That is the equation. The N here is the total number of objects or molecules or whatever it might be. I think the example I'm going to do next is dice rolls, so total number of dice rolls, okay, in our system. K sub B is Boltzmann's constant again. P sub I here is the probability of a given object or molecule occupying the ith state, okay? Or the ith category, or the ith energy level, right? So we've been talking about energy levels is what we care about. We'll do an example with dice where the different categories or states are, did you roll a 1, a 2, a 3, a 4, a 5, or a 6, okay, right? Doesn't have to be energy levels, although that's what we care about more. P sub I is also equal to the number in that level over the total number, right? That's our basic definition for probability. A couple of other things that we have to, maintain. The sum from I sub 0 up to t has to be equal to 1, okay? Total probability has to be sum to 1. The probability of any given state has to be less than or equal to 1. Just total number of categories you have, okay? So it might be 4 energy states, it might be the 6 different numbers on the die that you could roll. T is total categories that you have. So then, if the probability has to be less than 1, what would the natural log of the probability have to be? What's the natural log of a fraction? It's always a negative number, right? This is going to be less than 1. Actually, going to be less than 0. I don't know why I wrote it like that. The log of any fraction is negative, okay? Does entropy have to be positive? Entropy does have to be positive. Change in entropy does not have to be positive, okay? But if I have a multiplicity of 1, I have only one way of something happening. the entropy is 0. 0 is the bottom of entropy. Okay, there's either no entropy or there is some. There's no negative entropy. Now delta S could be negative, right? So S has to be positive. And so this explains the function of the negative sign up here, okay? Hence, negative sign in the equation. Because this whole term right here is going to be negative. What do you need? The natural log of a fraction is going to be a negative number. Okay, this is always going to be some positive fractional value. So this whole piece, I'm summing up a whole bunch of negative things. This is a number of objects or molecules. This will never be a negative value. Boltzmann is always a constant. So I need this negative here to guarantee that entropy is always a positive value. Now, delta S can be negative for your system or your surroundings, but not both. Or at least not both at the same time. Delta S universe can't be negative. So you can have like a local change in entropy that lowers entropy for your system, but that would mean it's going to be matched by some increase in the surroundings such that the overall universe won't have a negative change. So let's say we have, just the example we'll do for a negative change in entropy. So let's say we have, I think I drew this on the board the other day, didn't I? When I like drew it wrong. So these were, what are these? What am I drawing right now? Lipids. Lipid bilayer assembly. Okay. And then I inverted my my bilayer. So the polar groups are going to be on the outside. The head groups, here are all my tails that are hydrophobic interacting with each other. Okay. So this system here obviously has low entropy. Okay. So the change in entropy, right, final minus initial, is going to be negative, okay? But what we haven't considered, we're only considering our system as the lipid molecules themselves, okay? So we haven't considered our environment / surroundings, which is full of what? What is the surrounding of cells and lipid bilayers? What are we mostly made of? Water. Okay. We haven't considered H2O yet. Okay. And this is forthcoming. But again, just so you know, delta S universe equal to delta S system. That's delta S surroundings. Okay. This could be negative, or this could be negative, so long as this is still increasing overall. Okay. So the lipids can have a negative change in entropy, but that means the water and everything around it must have had an increase in entropy to accommodate it. So let's do our die example. Okay, rolling a die. So let's say I have, we'll do a non-energetic example, and then I'm going to go into the slides, and then I will give you an actual problem off of last year's homework and the previous semester's exam. We'll solve that one in teams and then take a break. And we can skip solving it, but I think that's what you guys want to do, right? Practice is better. Okay. So I have a dice here, and I have n number of them. Some number doesn't really matter. Okay? They are unbiased. Okay. They're six-sided. And the probability of rolling each number is equally likely. Okay. Given that information, calculate entropy. Okay. as, leave it in this form, S over N KB, okay, equal to the negative summation of the probabilities. So first of all, what is T? I already alluded to this. T is equal to 6. What's P sub 1? And P sub 2, they're all equal to 1/6, right? We said they're all equal. What are the units of this? That whole term. Unitless. Entropy is joules per Kelvin. Boltzmann's constant is joules per Kelvin. Number of things doesn't have a unit. Joules per Kelvin, nothing. Again, I will probably rarely ask you to do it in this form and leave it as NKB, but this is how the book has a lot of practice, okay? And I don't want you to avoid doing the practice, okay? In fact, if you can understand it a bunch of different ways, it's probably better for you. Okay, so this would be equal to negative the sum. All I did is take my probabilistic definition. These two terms were over here, right? I've just moved them. So this would be 1/6, the natural log of 1/6, okay? Plus 1/6 times the natural log of 1/6. So this was for category 1, rolling a 1, category 2, rolling a 2, category 3, okay? So on and so forth. So I'm going to sum this up over all 6 of my categories. So this would be -6 times 1/6, the natural log of the 6. This is equal to -6 times -2.986. If anyone wants to check me on the calculator, that'd be fine. 1.8, okay? Obviously that one was pretty simple because there weren't any differences, yep. Where?
You have -6 times -2.
Yeah, -6 times -2 is not going to make 1.8.
Yeah.
So
0.2.
here we go, 0.2. -0.2. Oh, there. See? Not to make anybody too sad right now, but there are definitely some answers on the quizzes that were not even conceivable numbers. Like your lungs can't be 3,000 liters big. That's way too big. My whole body, all my blood is like 6.5 liters, so there's really no chance that what's going on in here is 3,000. You'll get partial credit, don't worry. Your system consists of a large number of die, n unbiased die. The probability of rolling each number is thus equal to 1/6. Calculate entropy, and it's asking you to not plug in n. We don't know the number of n. I don't know the number of die that I have here. And you don't put Boltzmann's constant in. So first of all, why would entropy over n some number times Boltzmann constant be unitless? It's joules per Kelvin over joules per Kelvin. They're all going to drop out, okay? N doesn't have a unit. Joules per Kelvin over joules per Kelvin. T equals 6 in this case. P sub I, we have 6 categories. Each one is 1/6. I'm just calculating, I've asked you only to calculate this piece here. So what you would essentially be calculating here is 1/6 times the natural log of 1/6 plus 1/6 times the natural log of 1/6 plus 1/6 times the natural log of 1/6, all the way down, okay? I'd like to write it out, but again, in time, we'll just go through it quickly. All of the handwritten notes are, 1, already online from last semester, and 2, I can post them again in this semester's folder if it helps you, and on Monday, we'll run through a better example problem. Another thing I did last semester, I have no idea if students watched it. I would solve problems on PowerPoint and put audio over the slides. that's something people would be interested in listening to, I am happy to do that again. Okay? So the final answer here is 1.8. Okay. Why is this negative sign here? What is the natural? First of all of these probabilities have to be less than 1, right? They're going to sum to 1. What is the natural log of a number that's less than 1? It's always negative. So this is here to make my entropy be positive, okay? Entropy is never negative. Change in entropy could be. Delta S could be negative. S alone is never going to be negative. If you get a negative number, check your math again. Okay. So now we have a biased case, okay? You still have some n number of die. I don't know how many I have, doesn't matter. And some of them are spiked in a way where they give, I have red die that are biased towards a 2, and I have some green die that are biased towards a 4, and now there's these new probabilities of getting 1, 2, 3, 4, 5, or 6. These are the possible outcomes I can get, and they're no longer all equal to 1/6, but the probability of getting 1, 3, 5, and 6 is 0.1, whereas the probability of getting 2 or 4 is 0.3 now. Okay? Total probability still needs to equal to 1 if you sum all of these up. Without doing any of the math, what do you expect to happen to the value of entropy? It was 1.8 before. What do you think this number should be? Smaller. Why? It looks less random. This is a less even distribution, a less random distribution, a less disordered distribution. I'm going to get more 2s and 4s. Okay? So in this case now you would have 0.1 times the natural log of 0.1, and you can multiply that by 4, or you can sum them up each time if that makes you more comfortable. Okay, you would add that to 0.3 times the natural log of 0.3. Again, you can do that 2 times, or you can add that up separately for 1, 2, 3, 4, 5, 6. The final answer in your textbook is 1.64. It's lower than 1.8. It's what I expect. It's unitless because it's asked me to do this in joules per Kelvin over joules per Kelvin. Okay. So these are 2 different ways to calculate entropy based on statistics and probability. And again, the probabilistic definition is essentially kind of a Stirling's approximation for the statistical definition. So this is the one we saw before. You have 2 units of energy going into a system of 3 molecules. Okay? And these were the possible energy distributions that we thought through. Multiplicity of both of these was identical at 3. And we said, yes, these distributions are equally likely, right? So now for the ever so slightly more sophisticated system, I have 3 molecules and I put in 3 units of energy. What are the options for that? What's the easiest looking one? Just the fastest one to say maybe. 1 at 3 and 2 at 0. What else is there? 2, 1, 0. 1, 1, 1. Yeah, I think that captures all your choices. Okay. 1, 1, 1. Okay. All of them move up into the first level such that the total energy is still 3. Okay. They're each contributing 1. Here we have 1 jumping up to the 3rd level, 2 staying down in the 0 level. Multiplicity for this situation is 1. There's only one way to do it. Okay, multiplicity for this was 3, just like before. And in this case, where you have 1 molecule moving into the 2nd level, 1 is in the 1st level, and 1 stays in the ground state, there are 6 different ways for this to happen. Okay. Here's our multiplicity equation. So I wouldn't use this entropy calculation for only an n of 3 molecules. That's kind of too small. I also want to bring to your attention that number of molecules is a capital M here. Number of molecules is now a capital N over here. don't get hung up on notation. If you understand what we're doing, it doesn't matter what the letter is, okay? All right, so this is the most probable situation, right? This is the most likely case. And if you did your horrifically bad entropy calc without multiplicity and instead used this, you'd still see that this would have a higher entropy than these ones, okay? You could just do it with real multiplicity though. In situation C, how do I get P sub I for level 2? If I did want to use this and I wanted to calculate the probabilities, what is the probability? Yeah. It's just 1 over 3, okay? It happens to be the same for all of them in this case, right? The probability of the 0th level is 1 over 3. Okay. Probability of the first level is 1 over 3 here, because this is just equal to n sub I over total n's. From last time, what we did was we defined the probabilistic definition of entropy, and we also talked about how to do energy distribution calculations. Okay, so the probabilistic definition of entropy, it is a description of entropy written in terms of probabilities of the different outcomes for a system. Okay, for some system that has t possible different outcomes, and so the examples that we care about are t number of different energy levels, and an example we did last time was a t-sided die, right? We said a regular 6-sided die of equal probability of each side coming up. We did an easy entropy calc for that example. We also looked at this system here. Okay. So how many energy levels are there here? 11, technically. Ground state or 0 energy will always be the bottom, will always be the first energy level you will consider in any example problem, okay? U sub I is our notation to give us our energy level. So 0 energy is U sub 0. Energy level 1, U sub I has energy 1. Okay, we said it might be arbitrary units. Maybe I'll give you joules, could be kilojoules, could be whatever. Okay. The number of molecules that we have in the 0th level, n sub 0, is equal to 10. We can count them in a system this small. Okay. The number of molecules in level 1, or n sub 1, is 9. Okay. So n total is the sum of all of these 55. Okay. And if we want to calculate the total energy of this system, what do we do? Energy of the level times the number of molecules in the level, and sum it across all the levels you have. So the total energy for this system, U total, is the sum of n sub 0 times 0 plus n sub 1 is equal to 9 times energy level of 1, up to 165 energy units. How do I get the probability that any one of these 55 molecules is in the 3rd level? What is the probability of the 3rd level? So it is n sub 3, number in the 3rd level, over the total number, 7 over 55, which I don't know, is 0.127, right? So the probability of any given level is given by this equation here, just our general probability equation. Number in that energy level, total number of molecules we have. And if we want to just do a check for ourselves, make sure everything sums to 1, okay? So once we have all these probabilities, we can now calculate entropy for this system using the probabilistic definition, which looks like this, okay? And is somewhere on your equation sheet. All right, so S is equal to negative n, the number of total molecules, times Boltzmann's constant, times the sum over the T is the total number of energy levels I have going from ground state or 0 up to, in this case, 10. I really wouldn't have to include 10. I see that there's nothing there and probability of 0. Okay, I'll take the probability times the natural log of the probability of that level and sum over all of my levels, something like this. Okay. Negative 55 kb, 10 over 55 times the natural log of 10 over 55, plus 9 over 55, and on up across all the levels. The probabilistic definition is an approximation of the statistical definition, okay? It's suitable for very large values of n. So how come I don't need probabilistic definition for small values of n? Do I even need it for the system that's on the board right now? Not really, okay? Because I can do multiplicity of this system, all right? M factorial is 55 total things. The categories on the bottom, I have 10 factorial, 9 factorial, 8 factorial. So I mean, I can do this. None of these numbers require it, all right? So my expectation of you on the homework and on the midterm is that either the word probabilistic definition will be expressly stated so you know to use it, or you won't have a choice. The numbers will be so big, or an n won't be given. You'll just be given probabilities of levels, and then you'll be asked to give a relative measure of entropy. Leave it in terms of n, but you'll have to use the probabilities. It would be your only choice, right? Transfer between two systems, okay? System A, system B. What is the new U total when these two things come together? Total energy of A is 10. It's a 0 plus a 1 plus a 2 plus a 3 plus a 4. Here we have 0 times 3 plus 2 times 1 gives us a total energy in B of 2. So when we put these two things together, what will be the new U total? 12, right? Conservation of energy. That's my only choice. And then these are three different configurations, okay? What does that mean? What do these three different configurations represent? Microstates. These are different microstates of the same macrostate. The macrostate is 10 particles, total energy 12. Okay? So if you have two things that have the same total energy and the same total particles, then you have two, but they're ordered differently. The energy distribution looks different. They're still two microstates of the same macrostate. Okay? Same total particles, same total energy. Okay. What is the Q indicating? Heat. So when these two things come in contact, there's going to be some sort of heat flow between them. Remember, we were talking only about kinetic energy, okay? So these things are bouncing and gonna run into each other and exchange heat until there's no net change in heat flow. They reach equilibrium, okay, after a sufficient amount of time. So this state here that has higher energy, okay, has 10, is a higher temperature than our lower energy state. When they come in contact, heat will flow from the higher temperature into the lower temperature. The energy will be transferred through the collisions between the molecules, okay, until they reach some final temperature. And then just keep in mind that in reality we have both kinetic energy and potential energy, and right now we're just exclusively talking about kinetic. What's the multiplicity of the combined system at equilibrium? So let's start by, what is the multiplicity of A for this one? How do you go about doing that? Just side A. What goes on the top? A number goes on the top before the factorial? 10. What goes on the bottom? 2 and 8, okay? So the multiplicity of A is 45. How about for B? It's still 10. 6 and 4, okay? What is the combined multiplicity of this system right now given this information? Forget the words at equilibrium. And multiply them together, right? And I get 9450. No. Right now, stop and go. If I asked you the combined multiplicity of putting these two things together, this is how you would do it. You would just multiply them. Now, if you let enough time go by, they would rearrange themselves in order to maximize multiplicity. Okay? And that's what equilibrium is here. So they could organize themselves something like this. This would actually make multiplicity worse, so it wouldn't probably do this. Okay? So total energy in available levels stays the same. We still only have 2 energy levels that they can get into. We still have 10 total molecules being contributed from A and B. But given sufficient amount of time, the system would try to maximize entropy by making the highest possible multiplicity. Okay. The maximum entropy of a combined system after heat exchange occurs when equilibrium is reached. Two systems come into thermal contact. Okay. So we have 2 systems, A and B, and then they're going to come into thermal contact, meaning that they can exchange kinetic energy through collisions until no more net heat flow. Okay. Heat can still flow back and forth, but there's no net change. They've come to equilibrium. They've reached the same temperature. Okay. Temperature is a relative measure of average kinetic energy. Okay. So in these illustrations, we're assuming each energy level is associated only with kinetics. Okay. All of these molecules are, say, just a point for an ideal gas molecule. Okay? They don't have potential energy right now. So how would I get the average kinetic energy of, say, system A right here? It's the total kinetic energy, keeping in mind that I'm telling you these energies are only kinetic. It's 10, right? So we could sum it up. We could go, there's, n of 1 and 0, 1 times 0, 1 times 1, plus 1 times 2, plus 1 times 3, plus 1 times 4. This is also given to us. So the energy of the system is 10. If I divide it by the number of molecules, I5, the average kinetic energy of this system would be 2. 10 divided by 5. And the average kinetic energy of this system is 1 divided by 5, or 1/4. This system has a higher temp. It has a higher average kinetic energy. This system here has a lower temp, which they've chosen obviously to illustrate with blue as cold and red as hot. So straightforward. Okay, temperature 2 is colder, and when they come together, eventually heat will flow from the hot system to the cold through kinetic energy transfer until they reach a temperature that is going to be in between. And in this case, that temperature is the same for all of these, because total kinetic energy is conserved. Yep.
So is the total energy equal to the kinetic energy of small amount of time?
Yes, in this particular oversimplified case, I've said we're only considering kinetic energy, and all of these are a single point. They don't have anything else going on. They're just treated like a monoatomic ideal gas. I have a review slide that reminds you, FYI, real molecules have potential energy too. Okay. So yes, this is we're operating under the assumption kinetic energy is all that's here. And so you can run through and check this. These all have the same total energy, right? It's going to be 12 because these are, the wording in your homework will be they're isolated from the environment, meaning they can only exchange energy with each other, and the total energy will be conserved and no energy will be lost anywhere else. Okay, so they'll all have 12, and if you divide 12 by what is now 10 total molecules, you'll get 1.2. So you'll have this temp that's in between. These are 3 microstates of the same macrostate. They all have the same total energy and the same total number of molecules. U is the same and N is the same. Even if the energy is distributed differently, you have 2 or more microstates of the same macrostate. If these things are satisfied, they're the same across the board. How do you decide which of these microstates is most likely at equilibrium? And your choices are this one here, or this one here, or this one here. Left, middle, and right. Yes?
It's the one that minimizes.
So this is a great point. Minimizing energy is one goal. in sort of overall systems. They want to minimize energy. Now energy is the same in all of these though, it's 12, and it just is 12, okay? So they all still sum to the same total thing. So then what's the other half that we can consider? Maximizing entropy, okay? So you could run yourself through and do multiplicity of each of these systems, and see which one is highest and know that that's the one that would give highest entropy. You don't need to do that. You can just look at them. Yep.
So like, what if both energy and entropy differed?
Gibbs, welcome Gibbs. You're beautiful. 10-ish slides ahead of the game. Yep. Those are two things that are in competition, minimizing energy and maximizing entropy. Okay. So given what we have here, they're all the same energy, we'll think only about trying to maximize entropy. Okay. I won't give you the answer because it's essentially the same thing as one thing on the homework. So think about how to do that on your own without doing a calculation. And that doesn't mean do your calculation on a paper on the side and then write that on your homework without showing it to me. Yeah.
For the systems to be the same, is it possible that the energy levels are the same but they have different number of molecules?
No.
So
You need to be two microstates of the same macrostate. You have to have the same ends and the same total U. How you divide your molecules among energy levels to get the same total energy is fine, right? Because you can see here, 4 molecules are in the 3rd level, but 6 are in the 0. Looks different than this, looks different than this, but if you sum them up, they're all gonna have energy 12, and they all have 10 molecules. Okay, so systems are always trying to maximize entropy, right? But systems are also always trying to minimize their energy. And these two things are in competition. If all the particles of the system were able to minimize their energy, they'd all be in ground state. But if everything was in ground state, it would push entropy to 0. Okay? The probability of everything in ground state would be 1. The multiplicity would be 1. Okay? And so this is obviously not possible. Okay? So what Boltzmann's distribution does starts to talk about sort of the balance of these competing interests and how to handle both the fact that we have, we're trying to maximize entropy, but we also need to minimize energy. And then chapter 9 quantifies it with the Gibbs equation. And so again, we know that unfolding the proteins is more favorable here. We're increasing multiplicity. When we put in heat, we'll get this increase in multiplicity, this increase in entropy. However, this is a much lower energy state, okay? They're making all of these favorable non-covalent interactions when the protein folds it up. So from an energetic standpoint, it would much rather be folded into its native form. Let me see something. Okay. So Boltzmann gave entropy a statistical definition, sort of in terms of the likelihood or the probability of things being in a certain place. And of course, he said the most probable state is the one with the highest multiplicity. Okay. Boltzmann distribution describes the probability of finding the particles of a system in any one of various states, and that can mean a lot of different things. So it could be positions, okay? It could be dye positions in the beaker of water. It could be some sort of molecular arrangement. It could be a protein conformation, okay? And the one we are talking about right now is energy levels, right? So how are things going to want to distribute themselves among different energy levels? So it tells us the likelihood of, or the probability of molecules being in a particular energy level. Boltzmann distribution tells us what distribution to expect at equilibrium, okay? So the Boltzmann distribution is what things would look like if we had sufficient time and there were no net changes in macroscale properties, okay? But what you will see on your homework and on example problems that we do, I can ask you to calculate a probability for something that has not reached equilibrium, right? Those distributions just on that other slide where the molecules were, I don't even know, 1, 2, 4, 4, 1, 2. That's not what equilibrium looks like, okay? Doesn't matter. Just know that with equilibrium, things tend towards Boltzmann. Okay, but we can also have alternative distributions. So for very large numbers of molecules, it's nearly impossible to track all their states, especially both energy and position together, okay? And it's much easier to look at the probability. Here's the figure I tried to draw for you, okay? Right, so we have these discrete and quantized energy levels. The gaps between sort of a transitional or kinetic energy level are very small. A little bit of heat going in means the particles can move faster pretty easily, whereas actually rotating around bonds takes a little bit more energy. Doing any sort of like bond stretching in this water molecule is an even bigger sort of energy gap to overcome for that to happen. And exciting things into a whole new electron shell is really, really difficult. So these are drawn totally separately, sort of kinetic energy levels, potential energy levels. This is what they really look like when you sort of lay them together, okay? You have electronic shells are the bold lines, and then within them are all the different vibrational and rotational states in between. And energy total would actually be the sum of all of these things, okay? We will always simplify to just energy, okay? In this class, know that these different things go in to it, but we will have energy levels that I'm telling you go ahead and treat them as if some of this stuff is already encompassed in going from energy level 1 to 2 or 2 to 3. We're not going to distinguish each one. But real life molecules, you know, they have several different types of potential energy and kinetic energy contributing. And I know we've seen this figure before, okay? Where, you know, heat can go in just to changing kinetic energy, but it can also go to exciting molecules into higher potential energy levels. So given enough time, things want to tend to relax towards a Boltzmann distribution, okay? And the Boltzmann distribution is an exponential decaying function, okay? Where the lowest energy levels are going to be the most populated, and as the energy levels get higher, there will be fewer and fewer things in them, and it's exponential decay. And again, like I said, I can still ask you to do some calculations on a distribution that looks like this. You just know that with enough time, this is where things are tending towards, okay? Trying to move towards. If we have a large energy gap between states, okay, it's logical that the higher energy states will be even less populated, right, by molecules in the systems than if the energy levels are really close together, right? So getting from one translational state to the next or one rotational state to the next, those are smaller energy gaps than, say, a whole electron shell change, okay? These electronic gaps are really big. The system needs thermal energy to reach higher energy states, okay? So at a higher temperature, the higher energy states become more populated. So this term here is called Boltzmann factor. Recall that EXP is our notation for E raised to the. Like I said, it is an exponentially decaying function, so that's why we have our negative sign here. Here's our exponential function. Here's the negative sign for decay. U sub j would be the energy of the jth level. Okay. Kb is just Boltzmann's constant. And T is also temperature. Okay. So you can calculate a distribution at a given temp. And if you change temp, you have to look at the distribution again. Because as you have higher and higher temperatures, things can start to get into higher energy states than they could have before.
So is the T on the numerator or denominator?
The T is in the bottom. This is a negative U divided by KBT is the bottom term. Yep. What are the units of Boltzmann factor? There are none. That is correct. What are the units of, say, U? Joules. What are the units of KB? And we're multiplying joules over Kelvin by Kelvin. okay, on the bottom, so we get the temp to drop out, and then joules over joules drops out, and it is unitless. What happens to Boltzmann factor as U goes up? As U gets bigger and bigger, as the energy levels get bigger and bigger, what's happening to that whole term, Boltzmann factor? It's getting smaller and smaller, right? Because this is a negative. Okay? We have this negative number here, so e raised to a bigger negative number is going to be a smaller thing. Okay? What happens to Boltzmann factor as temperature increases? It gets bigger, okay? So as U goes up, it gets smaller. As T goes up, this whole term, okay, as T gets bigger, U over KBT gets smaller, but it's a negative, so it is a smaller negative number, okay? It's getting less negative, if you will. The whole term gets bigger, okay? So as energy goes up, it's harder to get into bigger levels. As temperature goes up, it gets easier, okay, to move up into higher levels. And this whole term is unitless. The number of molecules N at a particular energy level decreases exponentially with energy U of that level, okay? And that's what's being shown here, okay? So you have really big energy gaps. Okay? These are all just considered some energy times KBT. From 0 to 2 and 2 to 4, you have most of the molecules in the lowest energy level. And as the gaps get a little bit smaller, now you have 1, 2, 3, and 4, or now these are all half spacing, you see more and more molecules populating higher levels. Energy levels are like stairs, though very rarely are they ever regularly spaced like this. Okay, you'll just be given values for the energies to use, and they won't necessarily be evenly spaced. Okay, but as the steps were to become smaller, smaller delta U, the higher energy states get more populated. So the number of molecules in a given state is related to the energy of that state, sort of by this definition here. So you can look at this top term. This is Boltzmann factor, right? Now EXP is written as e to the, and this whole term's on the bottom, remember. So if I want to look at sort of the ratio of molecules in the second level versus the first, I can divide these two things, and I'll be able to simplify this to the difference in energy between the two. And so as this value gets smaller and smaller, this value over here is going to get bigger and bigger. So even if you don't know all the energy levels, you could still think about the relative number of molecules that would want to be in a given energy state, okay? If you can keep your even spacing assumption. This sort of falls apart if they're no longer evenly spaced. There's an error in the figure in your textbook that I want to point out. So here it's showing increasing temperature. It has low temp, intermediate temp, and high temp. The bar trend is accurate. As increasing temperature goes up, molecules are getting into higher and higher energy levels. What shouldn't be happening here is that they're also changing the energy levels, okay? These should be all identical on this y-axis. So this could be 0 to 16, 0 to 16, 0 to 16 every time. I don't know why it's shrinking, okay? Because what it needs to show is when the energy level spacings do not change, but you raise temp, you're still able to get into the higher ones. Okay. All right, so quickly, I want to get a few more things out before we stop. Boltzmann distribution, okay? Reminder, it tells us the probability of finding a molecule in a given energy level at a given temp, okay? And if you have a new temp, you need to do a new calculation. You need to know the available energy levels. And you may or may not need N total, okay? Keeping in mind that we always expect this. So the general form, sort of a general formula for describing Boltzmann's distribution, remember it's a probability. Sort of general formula, general function for this is P sub j is equal to a capital A e raised to negative beta times u sub j, where P sub j is equal to the probability of finding a molecule in the jth level, jth energy level, and U sub j is equal to the energy of that jth energy level. And capital A and this beta are constants. Now the reason I give you this form is because this general form of equation is super useful in a whole lot of other courses, other applications. You might see something that looks a lot like it elsewhere, right? It's just an exponentially decaying function. But what we're going to do in this class is we have a particular set of values for our constants that we're interested in, okay? So to define A and B for this class, right, we'll define, for our purposes. We have a couple other things we know. So we know that P sub j has to be equal to 1. T is the total number of energy levels we have, okay, starting from our ground state up to however many we have. The sum of all those probabilities better be 1. P sub j is also equal to the number of molecules in the jth level over the total, if we have that piece of information. We know that the sum of all the numbers, it's super whispery, it's driving me nuts. Okay. Give me my final 5 minutes, please. Okay. So the number of molecules has to equal the total if I sum over all of the levels. This is conservation of mass. Constant total number of molecules. And then I also know I have conservation of energy. So the number of molecules in a given level times the energy of that level, if I sum that up over all the energy levels I have, this will be equal to U total, constant total energy, conservation of energy, or first law. So then we define our constant A. What we're going to do is we're going to take this equation here. Actually, let's take this equation up here and apply the summation to each side of the general form. Okay. Also keeping in mind that this has to be equal to, once we apply the summation, equal to 1. The sum over all of the levels is going to be equal, the sum of the probabilities over all of the levels has to be equal to 1, and this would be equal to the sum over all of the levels. This is just being plugged in for this term here. So this is just being plugged in to this value right here. A is equal to e to the negative beta times u sub j. So I can rearrange this, I can pull A out in front. This would be equal to 1, okay? Then I can move this over to the bottom to get A by itself. A is equal to 1 over, this is the sum. So again, this is a generic form of the equation. This is a general formula for this type of equation. Okay. Our beta here that we're interested in for Boltzmann is equal to 1 over kBt, right? If we plug that in, we now have the sum over all of our Boltzmann factors for the different levels on the bottom, okay? This term is Boltzmann factor if we let beta be equal to 1 over kBt. Okay? The derivation of this beta term is on pages 364 and 65. And then we are going to call this term here Q, okay, or partition function. Q is called partition function. It is equal to the sum over all the energy levels we have. It is a sum of our Boltzmann factors for each energy level. Sum over all the levels that we have. One of the things I want to point out, this is Q. This is called partition function. Like I said, it's given by capital Q. This is the equation for it. This is called canonical form, or reduced form, general form, whole bunch of things. Okay. The form that we are going to use in this class, it's also the only form given in your book. What we will use, and this is new this year, so I really want you to pay attention to this. A lowercase g sub j, okay? This is a weighting factor. And what it does is basically if there are different ways to be in one energy level, okay? There's ground state, probably ground state, but maybe there are 2 ways to be in ground state that are equivalent, okay? This builds in redundancy or degeneracy. If there's a level that can be achieved in more than one way, we need to consider that 2 times or 4 times or however many ways there are, okay? And so we'll look at examples. The reason I draw your attention to this is in past semesters I've used a capital N sub j, which looks a lot like total number of molecules, okay? So we're moving to G, which is what you'll find on the internet, okay? And then the last thing I want to say before we go, we'll do examples where we actually calculate a partition function next time. But what partition function can tell us, okay? Partition function tells us how particles partition. What's up, guys? Oh, you're here, great. Give me 1 second. These are how they are like spread or divided over the accessible energy levels. Can you see this? Levels. At a given temp, right? This is important, given temp. Another sort of way to think of this is thermal accessibility. So at a given temperature, how can things distribute? And just, I want to reiterate, as temp goes up, U sub j over Boltzmann times temp goes down, but negative U sub j over Boltzmann times temp goes up. Okay. And we'll leave it at that for today. So, the equations for Boltzmann distribution. If I have a system with n molecules, and I have a series of energy levels, U sub j up to t number of levels, I'm starting at 0, always start at ground state. The number of particles n sub j that have energy U sub j of any given, the jth level, at equilibrium would be given by, here's that equation. This is the probability of a molecule being in the jth energy level. What's the probability that any given one of my double bonds is in any one of these states? And I might not know this. That's okay. I can still use the probability information. What is Q on the bottom of that equation? Yes. It's called partition function, okay? Q is partition function, okay? And it's given like this, all right? It basically looks like the tops, except for you sum over all of the levels. Q is partition function. It is a normalization factor such that the overall probability of finding a particle in any level will be, I should say, less than 1. Or when you sum them up, it'll still total 1. I guess some words are missing there. But if you think about it, this is sort of like the level, and then divide over the sum of all the levels looks a lot like just a probability calc, except we're taking into account energy, right? It's sort of, you know, the top of this equation is like the level of interest that I like care about over the sum of all the levels that there are. It looks a lot like a probability equation. It just happens to incorporate energy's temperature and Boltzmann. Okay. What was the name for this whole term here? E raised to the negative U sub j over kBt. There's a name for that term. Boltzmann factor. Great. U sub j is the energy of the jth level. T is temp in Kelvin. Okay. Make sure you convert. kBt is Boltzmann's constant in joules per Kelvin. Okay. And again, you may need, if I don't give this to you in joules, you may need to get into joules. If it's kilojoules, make sure you multiply through by 1,000. Always be minding your units. What are the units of partition function? Make it so it's unitless. Convert all your units so that everybody's going to drop out. Joules over joules. Joules over Kelvin times Kelvin, everything should be gone. The Boltzmann distribution helps us see which energy levels of a system will be occupied at equilibrium and for a given temperature. What happens to Q as temperature goes up? It goes up. Okay. Those are the only two options, up and down. So you got a 50-50 shot. The other way to let yourself do it is think through it. It's tough because it is a negative exponent and it's on the bottom of a division sign, so it's, you know, but stop and go, okay, if t gets bigger, this whole term, ignoring the negative sign, would get smaller, okay? The bottom of my quotient is getting bigger. So the whole term gets smaller, but it's negative, so it's getting less negative. It's actually getting bigger overall, right? It's a smaller negative number. Okay? The whole term gets bigger, e raised to a bigger thing is bigger. What that means is if I ask you to calculate partition function at a temp, and then I say, now you've raised the temp of your system, you have to recalculate Q. Okay? Partition function is for any given temp. If you're at a new temp, calculate Q again. All right? What happens if U goes up? What happens to Q if U goes up? Goes down. This one's a little easier. It's on the top. Okay. And what about as the weighting factors, G sub j, go up? It goes up. Okay? So know what happens to Q when any one of these things changes. The derivations for these equations are 364 and 365 in your book. They do not do weighting factors, but it's way more relevant for us from a molecular standpoint. So these are the only versions of the equations you have on your equation sheet. Okay? The book, they look identical. J sub g is missing. Okay? They consider 1 across the board. Everything is only possible in one way. Okay. So we've established how delta U and T affect molecular occupancy of the different levels, okay? As U goes up, or as the spacing, delta U gets bigger between levels, okay? Less levels will be populated. As T goes up, more levels will be populated that are higher. If you fix those things and you change the number of different microstates that satisfy the same macrostate, or the same macrostate being the energy level you're at, this is your weighting factor. So for this example here, okay, there's energy here and it's just 0 is the ground state. Epsilon naught is just the energy of the first level and 2 times that is the energy of the next level. What is the weighting factor, or G sub j, for the ground state? It's 4. How about for the first state? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 11. Is it 11? Yeah. How about for the next one? I don't know, it might be 27. I can't remember. I don't have it populated. You're counting the number of different ways to be at the ground state. Okay? I didn't put it in here, I gotta add it. There's a link to a lecture at Stanford University where they go through, like, he proves how to get every single one of these. And I'm like, ugh, don't think through them, that's way too much. Like, one of their example problems is like making you figure out all the ways that it could be, that you could unfold this like 6-mer toy model into the second state. No. What is n sub j? Or what is n? I have no idea, it's not given. These are the weighting factors for the different levels. The total number of these things I'm talking about isn't indicated anywhere here, right? So this version of partition function from your book is called canonical partition function, reduced form, classical form, a lot of different ways you might see it online, okay? And again, it's assuming that each energy level has exactly one configuration, right? We care about molecular partition function, right? It's much more practical for the systems we care about. And so it has a weighting factor to accommodate degeneracy, different ways to be at the same energy state. So here's a simpler, instead of the 6-mer model, it's a 4-mer. And if you go ahead, this is the compact form. If you break one of the bonds and open it up, there are 4 different ways to do that. You'd be in the first excited state, okay? So this whole first excited state is a macro state, and this one here is one of the microstates, right? Yes?
So we consider each energy level in the,
What's the other word? Yeah, that.
This.
Canonical, thank you. So each energy level is a microstate in that case?
Each energy level is a macro state, and each of those macrostates has only one microstate for this one here. Every level, there's a ground state, there will be a first state, there'll be a second state, and those are different states, but there's only one way to be in them, okay? This one has 4 different microstates that satisfy the same macro state of first excited energy level. Yeah. And this one, it's just treating all the weighting factors as one. This is the version from past slides that I used, and sub j was wildly confusing, given that it was also number of particles in the level. So I dropped that and went with what you'll find most often on the internet. So it's cool if you want to look at old materials, even stuff I put together, just be aware of what we're doing this semester. Right? So if you want to write Q for this one, here you go. Weighting factor for the ground state is 1. E is raised to the 9th. Ground state's always 0 energy. I don't really have to finish out kBt or temp here. Anything raised to the 0 is going to be a 1. 1 times the weight factor is always, the first term of Q is always the weighting factor of the lowest level, the ground state. Then there's 4 ways to be in the first state, times E raised to, my energy was just given as epsilon, I don't know what it is. I haven't been given to me, over kBt. Okay, but if I'm given different energies and different temps, I could go and start plugging this in and using this. What does degeneracy do to Boltzmann, which is the expected distribution, if you have our assumptions of even spacing? What does degeneracy do to Boltzmann distribution? It messes with it, and we don't know what that looks like. It depends on the system we're talking about. It depends on the nature of the problem we've been given or the nature of the model we've written for ourselves, right? The first 4 problems on the homework are, again, me saying, all right, if I knew the tasticity of a polymer would influence how it would fold and what type of energy it would have, how could I write a model for the energy distributions? Okay? And eventually you just do it with a computer anyway, but you know, degeneracy changes what happens to Boltzmann. What happens when the energy spacings are uneven? Same thing, it no longer looks like an exponentially decaying function perfectly like this, but these equations are still valid, okay? Go ahead and use them. What this is still describing is what the probabilities of the levels would look like. And now it's just taking into account that there are different values for you and there are different degeneracies for each level. But it'll still give appropriate answers for probability if you were to wait long enough and let equilibrium come. This will be better. All right. What's the first thing you did with this problem? You drew it. I love it. You knew that because I populated drawing. Great way to get an easy point. Okay. A system has 4 energy levels uniformly distributed at 3 times 10 to the negative 20th joules apart. Let ground state be 0. Does this line need to be here for you to know to write that the ground state is 0? No. That could be missing and you would still know to write 0 energy as your ground state every time. Okay. The populations of the energy levels are given by Boltzmann. This is the clue to go ahead and use the probability and partition function equations for Boltzmann that you've learned. Even if these things weren't evenly spaced, you can still apply those equations, right? It's not gonna be a perfectly like exponential decay up through all of the levels. But even if they weren't evenly spaced, you would still use those equations. They're still valid. Okay. So the relevant equations you can use, identify what you can use. Okay. Identify everything you know. T is 298 Kelvin. Okay. Do I have N or N sub J? What are my weighting factors? They're all 1. There's absolutely nothing to suggest they're not 1 here. Okay. The words given by Boltzmann are not necessarily the clue that they're 1, because like I said, using these equations with Boltzmann factor are relevant even when they have weighting factors involved, okay? But there's nothing in this information for them to be anything other than 1. What fraction of the particles are in the ground state? So what is it asking me for? Yes?
What would the wording be that would there is a weighting factor?
It could look vastly different depending on the nature of the problem. It could be something like, you know, let the end units on the trans double bond be the same such that there's, you know, every configuration looks the same. There's 2 different ways to be bent, something like that. Again, try the homework.
So for the 6, it would be 2, like 2.
This is 2, yep. Weighting factor was 2 for, I should have drawn these like going up, but yes, it was 2 different ways. And the language will say something like, there's more than 1 way to be this type, you know. But exactly how I'll phrase it, you'll have to read.
The raising the populations of the energy levels is just like referring to the probability
Yes.
of it being an energy level, not the degeneracy level.
Yes. Yes, the populations of the energies they're given by, that's the word is meant to be probability, like how they're occupied, the likelihood they're there. Okay, so what is it asking for in this first one? What variables is it asking for? I mean, it's technically asking for P sub j. What fraction of the particles is kind of a weird phrasing, but a fraction would be the number in the ground state over the total number. And the fraction of the particles in the first excited state, 25C, is the same as 298K. All this does for me is make sure I don't have to do partition function twice for 2 different temps. If these were different temps, you couldn't use the same partition function twice. And in this one, it's asking me for the fraction of the particles in first excited state, so n sub 1 over n. This was some notation that I did show last time on letting beta be this whole term 1 over kBt, just to keep things neater when you're writing out your work. It's totally, this should be raised to the 20th. It's totally up to you whether or not you want to use this type of notation or whether you want to write your numbers in every single time, whatever is easier for you. When you're doing your calculation, you still have to type them in, so you know, whatever makes it neater for you. But what you could do is then set this here and set up your partition function like this, okay? Weighting factors, G sub j are all 1. Okay. And this is 0, they're evenly spaced, so I've let epsilon be the spacing, 3 times 10 to the negative 20th joules. Again, to just make this look neater. Totally up to you, it's optional. Just as long as you know what you're doing and keeping track of things on your own. Okay. So then the next state is going to be, you know, 1 times epsilon, 2 times epsilon, 3 times epsilon, They're all times beta, which is 1 over kBt. We know that's in the bottom of our Boltzmann factor for all of these. So Q is equal to 1 plus E if you plug all of this in and do the math, to the negative 7.29, E to the negative 14.69, E to the negative 21.885. Partition function is 1.00068. These are really small numbers. Even this is a really small number, okay? As the energy levels get bigger, they start contributing to partition function negligibly. Eventually you could go, nothing's in that level. Even though it exists, the probability of being there is so low, it's essentially 0, okay? The first term pretty much carries everything in partition function. So for the ground state, now I'm using my probability calculation, okay, which is Boltzmann factor on the top, but in this case for the 0th state, it would be this whole term here, but it's 1 times e to the negative 0, it's just a 1 over partition function, 0.9993. For the first excited state, we have our next term. The 1 is gone again, but here's my weighting factor is here, okay? It's 1 e raised to the negative 3 times 10 to the negative 20th joules over, put in everything, plug it all in, 0.00007. Those are the answers to this problem. So then what is the probability of being in the second energy state? 0. If you add these two numbers together, you have hit 1. I don't know if they're rounded, I don't remember, but it's essentially 0, right? Any questions about that? All right, let's take a break.